Before a single cubic meter of concrete is poured, a city must be built in the wilderness. This logistics hub houses thousands of workers and millions of tons of steel, mobilizing for a decade-long battle against gravity. Every inch of the foundation is scrutinized. Geologists analyze core samples to ensure the bedrock can withstand millions of tons of water pressure. One hidden crack could spell catastrophe, so nothing is left to chance. To build in the riverbed, we must first move the river. Massive diversion tunnels are bored through the mountainside using computerized multi-arm drills, creating a new path for the water to bypass the construction zone. Precision blasting is an art form. Engineers wire the tunnel face with a calculated sequence of charges, designed to shatter the rock into manageable pieces without damaging the surrounding geological structure.
Copy that. Moving to the next hole.
Once the dust settles, the mucking out begins. Low-profile loaders and trucks operate in a tight loop, removing thousands of tons of debris around the clock to clear the throat of the diversion tunnel. To prevent collapse, the raw rock is lined with shotcrete, concrete sprayed at high velocity, reinforced with steel fibers. This creates a hardened shell, turning a rough hole into a structural arch capable of handling a raging river. With the tunnels ready, the river is blocked. A cofferdam is pushed across the channel, a temporary earthen wall that forces the water to change course, entering the tunnels and leaving the main riverbed dry.
Synchronize the second. Dump their massive loads, beginning the monumental.
For the first time in millennia, the riverbed sees the sun. Millions of tons of sediment are excavated to reach solid bedrock. You cannot build a megastructure on mud. The foundation must be anchored into the Earth's crust. Before concrete meets rock, the bond must be perfect. The bedrock is pressure washed and scrubbed by hand. Even a layer of dust could compromise the friction needed to hold the dam against the water's push. The dam is made of the mountain itself. A dedicated quarry blasts millions of tons of granite, providing the raw ingredients for the concrete. This is the start of a massive on-site supply chain.
Timed, sending thousands of tons of raw material cascading down.
Boulders are fed into the primary crusher, steel jaws exerting immense pressure to fracture the stone. This aggregate is the skeleton of the dam, providing the structural bulk that will hold back the reservoir. To reduce emissions and traffic, a dedicated conveyor system transports aggregate over kilometers of rough terrain. It runs 24/7, a silent river of stone delivering the necessary ingredients to the batching plant. Uniformity is key. The aggregate is washed and sorted into precise sizes, from fine sand to coarse gravel. The specific recipe of these stones determines the density and strength of the final concrete mix. The batch plant is the factory's heart. Here, cement, ash, and aggregate are stored in towering silos. Computer systems weigh each ingredient to the kilogram, ensuring every batch meets the strict engineering standards required for the dam. Concrete generates massive heat as it cures. To prevent thermal cracking in such a thick wall, we replace mixing water with flake ice. This chills the concrete from the inside out, allowing it to set slowly and evenly. Inside the drum, the chemistry happens. The ingredients traverse the transformation from loose rock and powder into a liquid rock. Once mixed, the clock starts ticking. It must be placed before it begins to harden. Speed is critical. The mix is dropped into specialized transport trucks that rush it to the crane pickup point. This is a continuous loop, feeding the hungry construction site thousands of cubic meters a day. At the pickup station, the concrete is transferred to huge aerial buckets. Each bucket holds nearly 20 tons of wet concrete. These are the vessels that will carry the liquid rock through the air to its final resting place. Spanning the valley are the Blondins, massive cable cranes. They act as an aerial highway, delivering buckets to any coordinate on the dam site. Pilots and control towers fly these loads with joystick precision, fighting wind and gravity. On the poor block, the receiving team waits. The bucket arrives, and with a pull of a lever, 20 tons of concrete are deposited in seconds. The empty bucket shoots back up, and the team immediately moves to spread the pile. Dam concrete is incredibly dry and stiff. Small bulldozers are lowered into the block to spread the piles. They work quickly to level the layer before the next bucket arrives, maintaining a constant rhythm of pour and spread. To remove air pockets, large vibrators plunge into the mix. They shake the concrete at high frequency, liquefying it momentarily to ensure it consolidates into a dense, non-porous rock. This step is vital for water tightness. Between layers, thousands of kilometers of cooling pipes are installed. Cold water will circulate through these veins for months, extracting the heat of the chemical reaction and preventing the massive block from cracking as it cures.
Once secured,
The dam rises in 3-meter lifts. Climbing formwork automatically jacks itself up the face of the wall after each pour hardens, creating the mold for the next layer. It's a self-climbing factory floor that ascends with the structure. The dam is built in separate blocks to allow for shrinkage. Once cooled, the tiny gaps between these blocks are injected with high-pressure grout, bonding the independent columns into a single, monolithic shield against the water. Embedded in the concrete are the penstocks, huge steel arteries that will funnel the river into the turbines. Precision welding connects these segments, which must withstand immense hydraulic pressure without leaking a single drop. Before the water rises, trash racks are installed over the intakes. These massive steel grates act as a filter, stopping logs and debris from being sucked into the penstocks and destroying the high-speed machinery inside. Month after month, the wall rises. It is a game of 3D Tetris, coordinating steel, concrete, and piping in a vertical ascent. The structure is now visible from space, a geometric wedge dividing the natural valley. The spillway acts as the safety valve. Its surface is finished to a mirror smoothness. Any roughness here could cause cavitation. Vacuum bubbles created by fast-flowing water that can explode with enough force to rip the concrete apart. At the base of the dam lies the powerhouse, a cathedral of energy. Here, the brute force of water will be converted into electricity. The tolerances change from meters to millimeters as we enter the era of precision engineering. The spiral case is the water's final approach. Shaped like a snail shell, it accelerates the water and wraps it evenly around the turbine, ensuring a balanced, high-velocity spin. It is then encased in concrete to lock it in place. The runner is the heart of the dam. Weighing hundreds of tons, this precision machine propeller is lowered with surgical care. It must spin with zero vibration while being bombarded by tons of rushing water per second.
Steady, we are almost aligned.
The turbine shaft transfers the power. It is aligned with lasers to within a hair's width. This rotating column connects the water wheel below to the magnetic generator above, the physical link between hydro and electric.
Coming into tolerance now, looks good.
The stator is a stationary ring of copper and steel. Technicians hand-wind thousands of copper bars into its slots. This is the catch net that will capture the magnetic field and convert it into high-voltage current. The final piece is the rotor, a spinning wheel of magnets. It is lowered inside the copper stator with an air gap of only a few millimeters. When this spins, it creates the magnetic field that drives the flow of electrons. The electricity generated is too low voltage for travel. Giant transformers step up the power from thousands to hundreds of thousands of volts, giving the electricity the pressure it needs to travel hundreds of kilometers to the city. In the nerve center, the control room comes alive. Miles of fiber optic cables feed data to these screens. Operators can control every valve, gate, and breaker with a mouse click, monitoring the pulse of the entire facility. Construction is finished. It's time to plug the drain. The diversion tunnels are permanently sealed with massive steel gates. With the escape route blocked, the river begins to back up behind the dam wall. The reservoir fills. Millions of gallons of water accumulate, pressing against the dam with immense force. The structure groans and settles, transferring the load into the canyon walls exactly as the engineers calculated. The spillway gates are tested. They open to release a controlled roar of water, launching it safely away from the dam's foundation. This proves the facility can handle the worst floods nature can throw at it.
Excellent work, everyone.
The command is given open intakes. Water rushes into the penstocks, falling vertically and gaining tremendous kinetic energy. The potential energy of the reservoir is about to become mechanical motion. The water hits the runner, and a massive shaft begins to turn. It accelerates to hundreds of revolutions per minute. The balance is perfect. A coin balanced on the housing wouldn't even tremble. The magnetic field is energized. The generator fights back against the water, converting the torque into resistance and flowing electrons. The dormant copper coils are now alive with high voltage. The frequency of the dam must match the national grid perfectly. The operator waits for the waves to align. Click. The breaker closes. The dam is now locked in step with the nation's energy heartbeat. Power surges out of the powerhouse, through the transformers, and onto the transmission lines. The energy of the falling water is now traveling at the speed of light to factories, hospitals, and homes hundreds of kilometers away. The river is tamed, but life goes on. Fish ladders allow aquatic life to migrate past the concrete barrier. Environmental flows are managed downstream to maintain the health of the river valley. While the world sleeps, the dam works. It provides the baseload power that keeps cities running through the night. It is a battery made of water and gravity, always ready, always on. It took thousands of hands to build this. Engineers, welders, drivers, and geologists. They have left a legacy in concrete that will stand for a century, a monument to human ingenuity. This is the result. Clean, renewable energy powering our lives. From the wild chaos of a mountain river to the steady light in a living room, the transformation is complete.
Modern city, a testament to civilization's endless demand for light and energy.
We have not conquered nature, but we have learned to work with it. By taming the river, we have secured water and power for the future. This is the modern megadam, a masterpiece of engineering.